Hey everybody, another frequently asked question we've been getting is about aromaticity and lone pairs, the different criteria of aromaticity, and also how lone pairs work in aromaticity when they're on carbons and then when they're on nitrogens and oxygens. There's been a lot of confusion about it, so hopefully this video will clear some of that up. There are three criteria that compounds need to meet in order to be aromatic. The first is that they need to be cyclic. Benzene is the quintessential aromatic compound. It's cyclic, meaning forms a circle or a ring, whereas something like hexane does not form a ring. It's not cyclic, therefore it is not aromatic. That's the first check. Pretty easy check. Second check is that every atom has to participate in resonance. In other words, there can be no sp3 carbons. sp3 carbons you can think of as like stop signs. They stop resonance electron sharing in aromatic compounds, so they prevent aromaticity. Let's look at a couple examples really quick of that. Let's look at this butadiene right here. Every carbon atom in here is sp2 hybridized. They're all participating in some form of carbon-carbon double bond. So I ask you, is this compound aromatic? No, it's not, because it's not cyclic. Kind of a trick question there, I led you into that one. It does meet rule 2, but it doesn't meet rule 1, not cyclic. Again, if we look back at benzene, every carbon atom in here is sp2 hybridized. They're all participating in some double bond, electron sharing in a pi orbital and a p orbital, and they are all trigonal planar molecular geometry. A compound like this is also not aromatic because these two carbons right here are not sp2 hybridized, or sp3 carbons, so they can't participate in electron sharing and conjugation of those pi bonds. The third criteria that aromatic compounds have to meet is they have to have 4n plus 2 pi electrons. Now, I remember when I first heard that, I was very confused. What is 4n plus 2? Why is there a math equation in my aromatic determination? Well, all we're saying is it has to have 4n plus 2 pi electrons, where n is some integer. So you just pick the number. The number could be 1, 2, 3. The number of n has nothing to do with how many electrons are in the molecule. You don't have to say, well, this molecule has 3 pi bonds, so n is 3. You don't have to do that. All we're saying is that n needs to be some integer. So in other words, and maybe in simpler terms, you just have to have 2, 6, 10, etc. pi electrons in your molecule. And where these numbers are coming from is different. We plug in different integers for n. So if n is 0, you get 2. If n is 1, you have 6. So if your molecule has 6 pi electrons or 10 pi electrons, and it meets the first two criteria, then it's going to be aromatic. Lastly, and kind of as a side note, the molecule also has to be flat. Most compounds that meet the first two rules are going to be flat, so you don't typically have to worry about that criteria, but sometimes you do, so just throw it in there as a note. If a molecule fails criteria 1 or 2, it's considered non-aromatic. So that's almost every molecule that exists is non-aromatic. Like the hexane we drew earlier, non-aromatic because it fails rule 1, it fails rule 2, so it's non-aromatic. That's very common. Not so common is if a molecule meets criteria 1 and 2, but rather than having 4n plus 2 pi electrons, it has 4n pi electrons. That means it's anti-aromatic, and those molecules are highly unstable. Let's look at a couple examples really quick, and then we'll move on to the real purpose of this video, which is how do we do with lone pairs on carbons versus nitrogens and oxygens? How do lone pairs factor into all this? We're not really talking about them so far, and we'll get to that in just a second. So again, we look at benzene as the stereotypical aromatic compound. It is cyclic, meets rule 1. Every carbon atom is sp2 hybridized, meets rule 2. And then rule 3, it has 2 pi electrons, 4 pi electrons, 6 pi electrons, 6 pi electrons. And we know that it has to equal 4n plus 2, the other side of this formula, in order for it to be aromatic. So if we solve this formula for n, you can see that we're going to get n equals 1. n is an integer, 1 is an integer, so this molecule is aromatic. However, if we look at a molecule like cyclobutadiene meets rule 1, it's cyclic, it's a ring, meets rule 2, every carbon in here is sp2 hybridized. But how many pi electrons does it have? It has 4 pi electrons, 4 pi electrons. And if we try and solve that for the aromatic equation, 4n plus 2, you can see that we get 2 equals 4n, n equals 1/2. Well, 1/2 isn't an integer. An integer is any whole number. So that's not true. But if we try and solve it for the anti-aromatic equation, we get an integer, n equals 1. That means that this molecule is anti-aromatic. You don't have to do this algebra every time. You can just say, how many pi electrons does it have? It has 2, 4. Well, 4, I know that 4 equals 4n. I can solve that using an integer for n, so it's anti-aromatic. I'm just showing you the math in case the n idea confuses you. All right, now we're going to move into our discussion on lone pairs. Let's first look at cyclopentadiene. Cyclopentadiene is very commonly used on the DAT for questions about aromaticity, and I'll show you why in just a second. Is cyclopentadiene aromatic? It meets rule 1, it's cyclic, but does it meet rule 2? Rule 2 states that every carbon has to be sp2 hybridized. These carbons are all sp2 hybridized, but this carbon, you can see, is bonded to 4 different groups. It's sp3 hybridized, so no, cyclopentadiene does not meet rule 2, it's not aromatic. However, say we lost one of these hydrogens, and the lone pair stayed on the oxygen. Now our cyclopentadiene looks like this, and there is still a hydrogen up here. I just didn't want to draw it because it gets a little crowded. Now our cyclopentadiene looks like this. Is this compound aromatic? Well, it's still cyclic, but is every carbon atom sp2 hybridized? Let me redraw this, and let me redraw it kind of from a sideways perspective. Here are 2 double bonds. Now this hydrogen, notice, is in the same plane as these other 2 bonds. It has a trigonal planar geometry. The interesting thing about carbanions is they'll actually put that lone pair up in a p orbital. They'll leave the rest of their molecular geometry to be trigonal planar and throw the lone pair up in a p orbital, making them sp2 hybridized, and then allowing that lone pair to resonate with the rest of the p orbitals in the molecule. I'm not drawing these lower halves of these p orbitals just because it gets crowded, but what that tells us is that these carbanions in these molecules are actually sp2 hybridized, so it does meet the second rule. That's something a lot of students have been confused about. This is an sp2 hybridized carbon, and it makes sense when you look at it from this angle. Okay, lastly, does it meet the 4n plus 2 rule? Well, how many pi electrons does it have? It has 2, 4. We just learned that these lone pairs are also involved in the pi system, so it has 2, 4, 6 pi electrons. This is aromatic, whereas its conjugate acid, the cyclopentadiene with both of its hydrogens, is non-aromatic. So one of the most frequently asked questions we get on the DAT about aromaticity is, why is cyclopentadiene more acidic than you'd expect? And it's because if this molecule is thinking, if I can just lose this hydrogen and retain these electrons in that bond, I can become aromatic and I'm way more stable that way. So cyclopentadiene is more acidic than you would predict if you neglected aromaticity. Again, that's a commonly asked question on the DAT. We learn an important rule from cyclopentadiene. That is that lone pairs on carbanions specifically, are in p orbitals, which is what we just showed here. And they're always included in our pi electron count. So when I ask you how many pi electrons does cyclopentadiene have, you have to count the lone pair. You say it has 2, 2, 4, 6. You have to count the lone pair. Now, that's not always true with oxygens and nitrogens, which we're going to get into in a second, but it's key that you understand that lone pairs on carbanions are in p orbitals and are always included in pi electron count. You don't have a choice. If the pi electrons are going to make the compound anti-aromatic, which is extremely unstable, doesn't matter. You have to count them on the carbanion. You don't have a choice. Now let's talk about nitrogens and oxygens. They're a little bit different. Let's look at another commonly asked about molecule on the DAT known as pyrole, and let's see if it's aromatic. Well, it's cyclic. Pyrole is cyclic. Is every atom sp2 hybridized? Can every atom participate in resonance? The interesting thing is the nitrogen in this pyrole is going to do the same thing as the carbanion up here. What I mean is it's going to keep its hydrogen trigonal planar and throw the lone pair up in a p orbital so it can participate in resonance. So yes, this nitrogen is sp2 hybridized the same way that this carbanion was sp2 hybridized up here. So it meets rules 1 and 2. How many pi electrons does it have? Yeah, it's the same thing as cyclopentadiene's carbanion. Has 2, 4, 6. Has 6 pi electrons. Great, it's aromatic. The same thing goes for oxygens. Oxygen, let's look at a molecule known as furan. The same thing pretty much as pyrole, but with an oxygen instead. Is furan cyclic? Yeah, it's cyclic. That's pretty clear. Is every atom sp2 hybridized, or can every atom participate in resonance? Yeah, this oxygen is going to do the same thing that the nitrogen and carbon have done in our previous two examples. It's going to put this lone pair in a trigonal planar bond, so that that lone pair is in the same place this H has been in the previous two examples. It's in a trigonal planar sp2 orbital, and then it will throw its second lone pair up into a p orbital, just like we saw up here. That lone pair can resonate with the rest of the pi electrons. So every atom is sp2 hybridized in furan, and how many pi electrons does it have? It has 2, 4, 6. Notice we don't count both lone pairs. You can't just assume that because there's a lone pair you have to count it. Remember, on carbanions we always include it. With nitrogens and oxygens the rule's a little bit different. We're going to include lone pairs if they help us meet aromaticity. If they don't, then we won't include them with nitrogens and oxygens. So in Mike's videos, he talks about how lone pairs on nitrogens and oxygens are flexible, whereas they're not in carbanions. And this is the idea he's getting at. On carbanions, you always include them in your pi electron count. You don't always include them in nitrogens and oxygens. You include them if it helps you reach aromaticity, if it helps you meet the 4n+2 rule. So here, we want to include these lone pairs because they're going to help us. Without them, we only have 4 pi electrons, but with them we have 6, which solves this equation, meaning that this becomes aromatic. Let me show you one more example that I think will make this principle even more clear. We're going to look at the molecule pyridine, some people say. Is pyridine aromatic? Well, it's cyclic. Does every atom have an sp2 hybridization? Is every atom able to participate in resonance? What this nitrogen is going to do is dictated by the fact that it's already involved in a double bond. It already has electrons in a p orbital. That's how it's able to make this double bond. So what it's going to do is similar to what we've seen in our other molecules. It's going to throw the lone pair into an sp2 orbital, keeping itself trigonal planar, because remember, it already has a pi bond here. It already has pi electrons. So it's not going to use its lone pair in aromaticity, because using it in aromaticity, using its lone pair in the aromatic ring would hurt the aromaticity. Let's check it with the 4n+2 rule to get an even better understanding of why. How many pi electrons does pyridine have? 2, 4, 6. Has 6 pi electrons, which we already know solves this equation and makes the compound aromatic. What if you included this lone pair? Well, then it would have 8, which does not solve the 4n+2 aromatic equation. It solves the 4n anti-aromatic equation. So if this nitrogen were to use its lone pair in aromaticity, in the aromatic ring, it would make it anti-aromatic. So that's the whole idea of what Mike's getting at when he says that lone pairs on oxygens and nitrogens are flexible. You can think of it as like the oxygen and nitrogen are deciding if they should use their lone pairs in the ring or not. If it helps the ring achieve aromaticity and meet the 4n+2 rule, then oxygen and nitrogen will put their lone pairs in a p orbital so that they can help the ring. But if using their lone pairs in this pi electron system would take the ring away from aromaticity and actually give it enough pi electrons to be anti-aromatic, they will not do that. You do not have that same option. You can't choose with a carbanion. With a carbanion, you have to include the lone pair in your pi electron count. Hopefully that clears up the confusion that some students have been having with this principle. Good luck studying and have a good day.